Hi everyone, my name is Sungkon Chang and this is a video abstract of the paper Average Number of Zeckendorf Integers. This work can be considered as a kind of generalization of Zeckendorf theorem. I was surprised at the Zeckendorf theorem at three different stages. The first one was that it's a really neat theorem and I didn't know about that until 2013. The second one was that the theorem was published in 1972. It feels like it should have been known a long time ago. So here's a picture of Edward Zeckendorf and the title of his paper, published in 1972. And the third one was the natural generalization I considered was not available in the literature. So let's take a look at the statement of the Zeckendorf theorem. So here's a defining a linear recurrence of a Fibonacci sequence, and these are the first two terms of Fibonacci sequence. So let me write down a few more terms of a Fibonacci sequence. Share those. So if you add 5 and 8, you get 13. So here's a statement of the Zeckendorf theorem. It says each positive integer is uniquely written as a sum of distinct non-adjacent terms of a Fibonacci sequence. Let me explain that inductively. Suppose a positive integer m is written as a sum of distinct terms and is non-adjacent, so it's the earliest term fn, and the next term is fk, and so on, where k must not be adjacent to that, so it's greater than or equal to n plus 2. When it is written in that form, we call a Zeckendorf representation. The fact that it's written as a distinct terms of a Fibonacci sequence, we say it is represented. So we want to know what happened to m plus 1. Can that be written in that form? It's all about what this fn is. If fn is greater than 1, then you can just put 1 in there. It could be adjacent to this fn, but we can use this linear recurrence to rearrange that into Zeckendorf representation. If it is 1, there's a room, f2 in here, so that you can simply change that as you add 1 to 2. So it's always written as a distinct terms of a Fibonacci sequence. Maybe its adjacent terms occur there, but again, you can rearrange it using this relation. Interesting part of this theorem is that it's uniquely written. And that's also an interesting part, and that concludes the statement of the Zeckendorf theorem. The very first generalization of Zeckendorf theorem I considered was the following. Let's keep the Fibonacci linear recurrence, but use different initial values. Almost all the times, these sequences do not represent all positive integers. So I asked myself if there can be a fast and efficient algorithm that determines if a given positive integer can be represented by these sequences. I thought it was a general natural question. I don't know the answer to this problem, but recently I asked myself a slightly different question. Given a positive integer x, what is the proportion of positive integer up to x that can be represented by these sequences? So let's take a look at a written formulation of this question. So here's a statement, the same linear recurrence of the Fibonacci sequence and potentially different initial values, and just to simplify the problem, I required the GCD of these two numbers to be 1. So given a positive integer x, how many integers up to x that is written as the sum of distinct terms of this new sequence? The first example I considered was simplest one that one can think of that is related to Fibonacci sequence is the one that starts with the 2 and 3 instead of 1 and 2. So all the terms is determined with these two values afterwards, so therefore it's precisely the same sequence as the Fibonacci sequence, except it is missing the first term 1 there. What is written down here are not just the terms of this new sequence, but all the integers that is written as the sum of the terms of this new sequence. For example, if you look at 11, and that is written as the sum of 3 and 8, and 3 is one of the Fibonacci sequence, so it is the terms of the sequence, and 8 is also the terms of the sequence there. And I counted up to 100. It turns out there's 62 of them. So the ratio up to that is a 0.62. And of course, I ran this x value, here is 100, a lot higher. It seems like the ratio is stabilizing to this number 0.618. When I was running this computer experiment, I had actually no expectation. I was just excited about this problem. I just wanted to run some result. But after I stared at this number a little bit, I realized that it's a part of the golden ratio. This number is precisely this -1 plus root 5 divided by 2, and golden ratio is 1.618. And if you add 1 to that, you precisely get the golden ratio there. At this point, I was very excited and actually very determined to explain why the golden ratio is involved there. So let me show you the statement of the result. So here it is. Turns out if you start with the G1 and G2, and if you use the same Fibonacci linear recurrence, the ratio turns out to be this number. And this asymptotic result is actually saying more than just a ratio. It's a big O of 1 expression is involved in there. If you start with a 2, 1, it generates everything as long as your initial value is not 2, 1, and we have this very general result. After I finished the case of Fibonacci linear recurrence, I pushed the technique to a slightly more general case called nth order Fibonacci sequence. While this paper was reviewed, the referees of the Journal of Number Theory suggested to go for even more general case. The technique worked. So now the result is stated for the general case of a linear recurrence. I really like to thank the editors and the referees of the Journal of Number Theory, and I thank you for watching this video.